In this video, we're going to look at the fundamental theorem for line integrals. And first, we'll just read what that says, and then we'll talk about what it actually means. So the fundamental theorem for line integrals says that let C be a smooth curve given by the vector function r of t, where t ranges between a and b. Then let f be a differentiable function of 2 or 3 variables, should say variables there, whose gradient vector is continuous on C. Then it turns out that the integral over the curve C of the gradient of f dot dr is f of r evaluated at b minus f of r evaluated at a. And this looks very much like the fundamental theorem of calculus part 2, where you just plug in your upper bound into your original function and you subtract off plugging in your lower bound. And that's essentially what ends up happening here, but let's actually go through the proof for that. So the proof is, well, the integral of the gradient of f dotted with dr is the integral from a to b, where again t ranged between a and b. The integral from a to b of the gradient of f of r of t. This is r of t. So we just plug in r of t into our gradient of f function, right? Because r is some parametrization of the curve that we're traveling around. So we plug that into our gradient of f, and we dot this. What was dr? Dr was r prime of t dt. So we dot gradient of f with r prime of t dt. And what is that? Well, we get the integral from a to b of, and the gradient of f is partial of f with respect to x, partial of f with respect to y, partial of f with respect to z. We're dotting that with r prime. So, and r prime is dx dt, dy dt, dz dt. So that dot product is just partial of f with respect to x times dx dt, plus partial of f with respect to y times, and actually this should be partial y with respect to t, same here, partial x with respect to t, and plus partial of f with respect to z times partial z with respect to t. I'm lying, those should be d's, not partials. All right. And all of that is equal to, of course, the integral from a to b of d dt f of r of t dt. And when I said of course, I just mean if we remembered that this is our chain rule. So this is the chain rule of f of r of t. So we take the derivative of f of r of t. This is exactly what we get here by the chain rule from back in chapter 14. Okay, now how do we integrate that? Well, we take the integral of the derivative of something with respect to t, right? This is the derivative with respect to t. We integrate with respect to t. So the integral of all of that, just by the fundamental theorem of calculus, gives us exactly f of r evaluated at b minus f of r evaluated at a. And that actually concludes our proof for this fundamental theorem for line integrals. Now, what does this really say? This really says that if the f, the vector field f, is actually a conservative vector field, i.e. there exists some scalar function f, that the capital F here is the gradient of that scalar function f. If that is true, then the integral depends only on the value of the scalar function f at the endpoints of our curve C. Okay, well that gives us a fantastic way to solve these line integrals over vector fields if our vector field happens to be a conservative vector field. So let's go ahead and see an example of that here. Okay, so we're going to do an example where we evaluate f dot dr over a curve C, where C is the arc of the parabola y equals 2x squared from negative 1, 2 to 2, 8. All right. Well, first we notice, and where f is x squared I plus y squared j, or in other words, the vector written out in this vector form, x squared, y squared. Okay, so first thing we'd like to note is that the vector field f really is the gradient of some scalar function f. And that is true when f is 1/3 x cubed plus 1/3 y cubed. Remember, the gradient is, in the first component, the partial of f with respect to x. So what is the derivative of this with respect to x? Well, we get exactly 3 times 1/3 x squared, or in other words, x squared, plus 0, because this goes to 0 when we derive with respect to x. So that's our first coordinate, x squared. And then we derive this with respect to y, and we get, similarly, y squared. So, this vector field really is the gradient of this scalar function f. So, by our fundamental theorem for line integrals, the integral over the curve C of f dot dr is just f evaluated at r of b minus f evaluated at r of a, where f is this function here. Well, r of a is our initial point on this curve, which was negative 1, 2. r of b was the end point, which was 2, 8. So we evaluate f at 2, 8 and subtract off evaluating f at negative 1, 2. And we just do that calculation. So we plug in, all right, we have 1/3 of x cubed, so 2 cubed, plus 1/3 of y cubed, minus evaluating this function f at negative 1, 2. And we put all of that in and we get 171 as our final solution. And that's where we'll end this video.